Imagine our universe, but instead of stars and galaxies, it's filled with data points. Each point represents a piece of information, like the color of a car, its speed, or its price. Now, imagine trying to understand this universe if each data point has not just 3 dimensions, length, width, height, but many more. This is the challenge of multidimensional data. It's like trying to see the entire universe at once. Think about shopping online. Each product has many features, like size, color, brand, and price. Doctors use multidimensional data to diagnose illnesses, looking at patients' symptoms, medical history, and test results. Even understanding the weather involves multidimensional data, with temperature, humidity, wind speed, and precipitation all playing a role. Visualizing multidimensional data is like creating a map of this complex universe. It helps us see patterns, relationships, and insights that would be hidden otherwise. Just as astronomers use telescopes to explore the cosmos, data scientists use visualization techniques to explore the multidimensional universe of data. One way to explore the data universe is through direct visualization. This is like using a powerful telescope to observe individual stars and galaxies. Direct visualization techniques allow us to see the data points and their relationships directly. One such technique is the scatterplot matrix. Imagine a grid of telescopes, each showing the relationship between 2 different dimensions of the data. This is what a scatterplot matrix does. It allows us to see how different dimensions are correlated. For example, how the price of a car relates to its fuel efficiency. Another useful tool is parallel coordinates. Imagine a series of parallel lines, each representing a different dimension. Each data point is then represented by a line that intersects these parallel lines, showing the value of each dimension for that point. These direct visualization techniques provide a powerful way to explore the multidimensional data universe. Sometimes the data universe is simply too vast to explore directly. In these cases, we need to shrink the universe down to a manageable size. This is where dimensionality reduction techniques come in. They simplify the data by reducing the number of dimensions while preserving the essential information. These techniques are essential for dealing with high-dimensional data, where direct visualization becomes impractical. They allow us to see the overall patterns and structures in the data, making it easier to understand and interpret. Dimensionality reduction techniques provide this big-picture view, making complex data more manageable and understandable. They are essential tools for any data scientist exploring the multidimensional universe. One of the most popular dimensionality reduction techniques is principal component analysis, or PCA. Think of PCA as the cosmic cleanup crew of the data universe. It tidies up the data by finding the most important directions of variance, the directions where the data points spread out the most. These directions are called principal components, and they represent the most important features of the data. PCA then projects the data onto these principal components, effectively reducing the number of dimensions while preserving the essential information. It's like creating a simplified map of the universe, showing only the major galaxies and their relative positions. PCA identifies the most important dimensions of the data and focuses on them, discarding the less important ones. This makes it easier to visualize and understand the data. PCA is a powerful tool for simplifying complex data and making it easier to visualize. By focusing on the most important features, PCA reveals the underlying structure of the data universe. Section 5, LDA, separating stars and planets. While PCA helps us understand the overall structure of the data universe, linear discriminant analysis, or LDA, helps us distinguish different types of objects within that universe. LDA aims to find the best linear combination of features that separates different classes or groups within the data. It's like drawing boundaries between different regions of the universe, separating galaxies, star clusters, and nebulae. LDA identifies the features that best distinguish different groups within the data and uses them to create clear separations. LDA is particularly useful when we want to classify or categorize data. By highlighting the differences between groups, LDA helps us understand the diversity of the data universe. It can be used to distinguish between different types of customers, diseases, or weather patterns. Section 6, MDS and Manifolds, Universal Mapping. Multidimensional Scaling, MDS, and Manifold-Based Visualization are like creating advanced maps of the universe, preserving the distances and relationships between objects. MDS tries to preserve the distances between data points when projecting them onto a lower dimensional space. Imagine creating a two-dimensional map of the Earth that accurately represents the distances between cities. Manifold-based visualization techniques like isometric feature mapping, ISOMAP, and locally linear embedding, LLE, take this a step further. They assume that the data lies on a lower dimensional surface, or manifold, embedded in a higher dimensional space. Think of the universe as a vast sheet of fabric folded and crumpled in multiple dimensions. Isomap and LLE try to unfold this fabric, revealing the true underlying structure of the data. These techniques are especially useful when the data has a complex, non-linear structure. They allow us to see the true relationships between data points, even when those relationships are hidden in the higher dimensional space. Section 7. Measuring the magic quantitative criteria. How do we know if our map of the data universe is accurate? Data scientists use quantitative criteria to evaluate the quality of their visualizations. These criteria help us determine how well the visualization preserves the original structure of the data. Spearman's coefficient measures the correlation between the distances in the original high-dimensional space and the distances in the lower-dimensional visualization. A high Spearman's coefficient indicates that the visualization preserves the distances well. König's topology preservation measure assesses how well the neighborhood relationships between data points are preserved. It checks whether points that are close together in the original space are also close together in the visualization. These quantitative criteria provide a way to objectively evaluate the quality of dimensionality reduction techniques. They allow us to choose the best technique for a particular dataset and ensure that the visualization accurately represents the underlying structure of the data. Section 8. Conclusion: to infinity and beyond. Just as astronomers continue to explore the vastness of space, data scientists continue to develop new and innovative ways to visualize multidimensional data. From direct visualization techniques like scatterplot matrices and parallel coordinates to dimensionality reduction techniques like PCA, LDA, MDS, and manifold learning, these tools allow us to explore and understand the complex universe of data. These visualization techniques are not just for scientists and engineers. They are essential tools for anyone working with data, from business analysts and marketers to doctors and educators. They empower us to make informed decisions, discover hidden patterns, and gain deeper insights into the world around us. As the volume and complexity of data continue to grow, so too will the importance of multidimensional data visualization. By mastering these techniques, we can unlock the secrets hidden within the data and embark on a journey of discovery to infinity and beyond.